Welcome back to Computer Science 4300. Today, we are here and we are going to be discussing Assignment 2. So Assignment 2, second assignment in the course. The first assignment was all about just getting used to C++ and SFML, versus Assignment 2 is all about actually making our first game. So I'm super excited because of that. Making our first game is going to be pretty awesome. So what I'm going to do is I have a couple of slides here about Assignment 2, and then I have the README file that I'll go through, and then I'll go through the code in Visual Studio here for the assignment itself. But before that, let me just quickly show, I've got some files over here, the solution to Assignment 2, and the type of game that we'll be making. So I've called it Geometry Wars clone because there's this game called Geometry Wars that I've played before. Let me see if I can get this. This is in a window, but it's actually, let me try and full screen that. Does this work? Might take a second. Let me really quickly try and figure out why that's not going ahead. Oh, it might be this. Perfect. Okay. So whenever I run the game, it's actually in a window, but I've just got OBS here, the scene set up to play that in full screen so you can see it better. So here's the game that we're making. It's very much like the game Geometry Wars, if you've ever played that. And so I'm controlling, actually let me restart it. I'm controlling this player object here in the center. We've got a little checkerboard background. And wherever my mouse is, when I click there, it will shoot toward that location. We've got enemies here that are all these differently colored shapes, and they're spawning randomly within the level. And when I click and when I shoot it, they explode into several different enemies of the same color and the same number of sides. So for example, if I shoot this blue triangle, a triangle has 3 sides, so it will explode into 3 smaller triangles. Versus if I shoot this green square, it will explode into 4 smaller squares. And those squares will fade over time until they eventually disappear. So the point here is to get as many points as possible, right? It's just to create this game with some basic physics, and if I die, I restart back in the middle. So it's a pretty simple game, but there's actually a lot going on behind the scenes, and the specification of an actual video game can take a little while to express in perfect detail. So while it only takes me a few seconds to really show this game and the game mechanics, it will take a lot longer to explain it in full in terms of game programming and our programming document. And then I'll go through the code to show you how you're actually going to be implementing this game. Okay, so that's a pretty good intro to the game. You can see what the game is all about. So let's close that down and we will get into some slides. So the first thing before I explain the assignment in detail, I wanted to go over the architecture that we are going to use for Assignment 2. So in Assignment 1, we were just getting used to C++, your first time possibly programming in C++, your first time using Visual Studio and the compiler, as well as the API, the standard library, as well as SFML. And in Assignment 1, all of the functionality of the entire program is just in this one main.cpp file. So that was really the bare bones, how do we get animations up and running, and how do we draw things to the screen, etc. In Assignment 2, we're going to do a lot more than that. So now that you're used to C++ a little bit, and you're used to the structure, and you've used Visual Studio, we're going to dive right into making some games. So in Assignment 2, we are going to have the separation of functionality into classes. We're going to write our own Vec2 class for 2D game math. Now we're starting to see the appearance of these ECS classes. So we're going to have entities, we're going to have components, and we're going to have systems. We're going to have an entity manager that handles all the entity data, and we covered the entity manager in the last class and what it's used for and how it's implemented. And the ECS systems functionality is all going to be implemented in functions in our game class. All right. So what we're going to have for this assignment is the following architecture. So a little bit of UML for you here. We're going to have our main game class. So, and this will become more obvious as I dive into the code, what's going on here. I'll explain all of this, but this is just an overview of the system and all the classes that we have. So we have first the main game class. This game is going to do things like store the window. It's going to store the entity manager. It's going to store the player. For example, it's going to say whether or not the game is currently running or whether it's paused, etc. It's going to have an update function, which gets called 60 times per second. We're going to run our game at 60 FPS. And we're also going to have a number of systems that implement the logic for the gameplay mechanics. So for example, the movement system, user input, rendering, etc. Inside the game class, we're going to have the entity manager class. So the entity manager class is going to store our vector of all entities. It's going to store our vector of things to add due to delayed effects. It's going to store our entity map. So all the things we talked about with the entity manager are going to be stored within the game class. Then we have the entity class, and it has the same structure as we talked about in the last class. However, we're going to have several different components in order to implement our entities for assignment 2. In order to implement this game, we're going to have a transform component, a shape component, a collision component, an input component, a score component, and a lifespan component. So those are the things, and we'll get into details about those when we actually dive into the assignment code. So for example, the transform component is going to store the entity's position, its speed, its scale, its angle, etc. The collision is going to have a radius as a floating point number, and maybe the score is like an integer. But I'll get into those details when we actually open up the project. And then we're going to have the vec2 class, which we've also talked about in some detail now. And I'm going to give you the header file or the skeleton code for the vec2 class, and you're going to implement the actual functions that we're going to need to use for this course. So vec2, see the previous lecture for the details of vec2. Oh, I have slides on this. Well, I forgot about that. So the components are going to be pure data. They're going to be stored in the entity class, and each component is going to be its own separate class. And intuitively, each component is going to be attached to a feature that we want to have an entity to have. And again, an entity has this structure. So an entity is any object within the game that we can give a position to or move around or interact with. It's going to store component pointers. So here we're going to have shared pointers to our components. The tag is going to be like the type of the enemy. So that will be the like it'll be a player or an enemy or a tile or whatever. Active is whether or not this this entity is alive or dead. ID is the integer identifier, and over here in the UML I've put a star here, which normally would indicate a raw pointer, but those are going to be shared pointers because I ran out of horizontal space to actually put this on the slide. The entity manager, that is the factory class for our entities. We are implementing delayed entity add and delayed entity removal for to solve iterator invalidation. And we have a secondary map from tags to entities, which trade storage for convenience and runtime. So I have a question over here in the chat. Why are transform, shape, collision, and other components shared pointers? Isn't entity a pointer already, so they're not going to be copied anyways? So that question, I would recommend going back and looking at the previous lectures, because we explained exactly why we're using shared pointers in this class. So I just don't want to take more time during this lecture to explain that, but it's all there in previous lectures. And the entity manager can also do like bookkeeping and memory management and stuff like that. We'll get more into the memory management side of things in a future lecture though. And then the game class is a top-level game object. It's going to store somehow all of the game data, and all the game system functions are going to be there as well. The gameplay code is going to be there in the form of systems. So all of the things related to our game at a top level are stored in this game class, and it's very important. So what can this game engine do? So the game engine as it stands right now as of assignment 2 can do the following things. It can create game objects as entity instances. It can add components to entities. It can implement gameplay via systems, and it can handle user input. It can pause the gameplay or exit the game, and it can initialize and load a configuration from a file. Okay, so that's what it will be able to do at the end of assignment 2. Now, you might say, well, that's not a very full game engine. Well, you know, we're going to get there over time, but it does have some limitations. So it can only display one scene, so we can only really play one type of thing at a time. We currently can't load any texture or sound assets. I mean, we could, but not in a really nice way. We can't display any textured animations yet. We don't have any menu or interface, okay? So what do I mean by a scene here? Well, a game scene, games can contain a bunch of different scenes, okay, that have very different logic and controls. So for example here, I've got a Pokemon example where there may be several different scenes. So maybe we have a menu or a dialogue scene up here in the top right. Down here we have like an overworld map scene. And on the bottom, we have a combat or a battle scene. So games can have many different scenes which contain very different logic and also contain like different controls and different graphics and stuff like that. And so in future assignments, starting with assignment 3, we're going to be implementing a bunch of these things. So in assignment 3, we're going to be able to load textures, we're going to be able to play animations, and we're going to be able to have multiple different scenes. Okay, and so I just talked about that, and the game class for assignment 2 will handle all of the functionality for our game, and some of the functionality will remain the same. Actually, I'm not going to go into this yet. I think I had this this slide here by accident, so I'm just going to remove that slide. So just realize that in the future, we're going to have different game scenes that we'll be able to implement starting in assignment 3, but not for assignment 2. Okay, so we saw assignment 2 and what it can do. So let's go over the README file for assignment 2 now, which is like an actual specification of the things that you have to do for the assignment. So let me just resize this before I bring it up. Okay. Perfect. So, a little slight change in the submission versus assignment 1. In assignment 1, you just submitted one file. In this assignment, you're going to zip and submit the entire source folder of the assignment. So I'm going to give you a source folder that contains multiple files. You can actually see these files in the background right here. You are going to be editing multiple files for this assignment. So what you're going to do is you're going to right-click the source folder, and you're going to zip it, and you're going to submit that zip file for your assignment. You are not allowed to add any files in addition to the ones already in the source folder for the assignment zip file. So this means you will not be submitting any changes that you may have made to the Visual Studio project. So what this means is basically the way we're going to mark your assignment is by importing this into our own Visual Studio project, and we don't want to have to change too many things. So you're allowed to put whatever code you want inside the files that we give you, but for this assignment, please do not make additional files, okay? Because they won't be submitted to us. Only the files that were submitted to you and edited are going to be sent back to us. You must include the following comment at the top of main.cpp. So this is the same as assignment 1. Just make sure that all of your group members' names and stuff are there. And if you didn't get anything to work, try and explain to us what you didn't get to work and why, and we can give partial marks for that. Okay, so on to the program specification. Let me quickly run this game again, just so you get another feel for this. So again, you are a player, you're moving around with the W, A, S, and D keys, you're shooting, and you're interacting with enemies. They can hit you, they can kill you, and you have a score, okay? And enemies explode. So that's the game at a very high level, but let's explain all of that now in excruciating detail, so you will have absolutely no questions when it comes to implementing the assignment. All right. So the player is represented by a shape which is defined in the config file. And I'm going to go over the config file at the end. So remember, assignment 1, we had a configuration file. Assignment 2, we also have a configuration file. But there's some more stuff in this configuration file. So the shape that the player is going to be is represented by that file. The player must spawn in the center of the screen at the beginning of the game and after it dies. So whenever it collides with an enemy, then it's going to die and be transported back to the middle of the screen. The player moves at a speed which is read from the config file in these directions. So W is up, A is left, down is S, and right is D. So the standard W, A, S, and D keys are going to move you around the map. And the player is confined to move only within the bounds of the window. So this means if I move all the way left and all the way down, I'm going to hit the edges of the window, and I'm not allowed to move outside the edges of the window. So you have to implement that. The player will shoot a bullet toward the mouse pointer when the left button is clicked. The speed, size, and lifespan of those bullets are read from the config file. So all of the things that we can possibly fit in the config file are going to be in the config file. Okay. Special ability. All right. So you are free to come up with your own special move, which is fired by the player when the right mouse button is clicked. So the right mouse, you click that, and you have to fire a special ability. What that ability does is completely up to you, okay? So the special ability is going to be worth 10% of the assignment. However, it has to follow these guidelines. So whenever you press it, multiple entities are going to be spawned by this special move. So you can't just fire one bullet, okay? It's something interesting has to happen. Multiple things have to be fired. The entities have to have some unique graphic associated with them, so they can't look just like a bullet. What you are going to do is you are going to have a unique game mechanic, that isn't in the other specification, and you're going to make your own component, a new component, or multiple components maybe, that implement this game mechanic. And you must have a cooldown timer implemented for the special weapon, okay? Must be implemented. And what this means is you just can't spam your special weapon. You've got to right-click it, and then some timer counts down before you can shoot it again. And the properties of the special move they do not go in the config file, okay? So just be aware that all of your special move stuff should just be hard-coded. Now, what do I mean by a special move? Well, luckily for you, I have some previous year's examples of special moves that I want to show you. All right, so let's go through some of them now. So these are assignment 2 student-submitted solutions for the special ability that were submitted in previous years. Okay, so here's one. I'm just trying to find the executables. All right, so this one is called Grenade Lob. So when I right-click on the map here, it's going to look like I lob a grenade at that location, and then it explodes. See how that works? So this is like some group completely came up with this, and you can see how, like, you know, the circle grows over time. And actually, I've run out of grenades now, so I would have to do that again. So this is one of the ones that I really liked. It's just a grenade lob, and when the grenade hits, it explodes, and all the things go out. That's pretty cool. I like that one. This one here is called It's High Noon. I guess this is a McCree from Overwatch reference. So I'm going to let a few enemies spawn that you can see what this one does. I'm just going to let a few more spawn. Okay, so I'm going to right click, and it sends out, like, it freezes enemies in place and then sends out a special move that kills those enemies. Okay, and it freezes them in place. So that's like High Noon from Overwatch. This one is called Post-Production FX. I'm not sure what this one does. I haven't looked at it. Okay, so this one, they added some special effects to the shapes, and I guess they didn't have a special move for that one. Okay, so that's just cool effects that they were showing off. This one is called Relevant Game.exe. I can't remember what this one does. Okay, so this is funny. When you shoot the special weapon, it comes back and kills the player. So I guess this was these super weapons are backfiring on the player, and so the super weapon is the imposter, an Among Us reference. That's pretty nice. This one is called... So this one kind of went above and beyond. This one has desktop audio, so I'm gonna play the desktop audio. So this group like went crazy and had a background, and they also have sound effects, and the tether shot is really cool. So when I right click, it's going to turn everything slow motion. Okay, so it's slow motion, and when I release right click, it's going to tether the shot to an enemy, and when I hit right click again, it swaps places with the enemy. So there's all sorts of crazy stuff that you can do. It looks like a simple game at first, but some of the bonus stuff that people have done is really incredible. And just thinking about how you would implement this sort of like time slowing stuff, it's really cool, and it's actually really easy to do this with ECS, okay? So go crazy with your bonus features. I think that's how you really learn in this course. This was a particularly cool one. Let me show a couple of others. This one had teleportation, I believe. Yeah, so this one, when you right-click, the player teleports and spawns bullets from where it used to be. So that was also a neat one. This one is a spiral weapon. Oops. So this is a spiral weapon. The bullets follow a spiral path, and I can shoot this one really quickly, and the bullets go around from where they were shot like that. That's a pretty cool effect. This one allows you to have up to 5 bouncing balls. So you can just have these bouncing balls around the room that bounce off the corners and interact with enemies, etc. This one is really cool. This was really clever. Your special weapon spawns another copy of the player that is also controlled by the mouse. Okay? So here I spawn... Oh, geez, I gotta stop dying. This one, so if I right-click, I'm spawning multiple copies of the player, and then when I move around and shoot, all of the players interact. And you might think that that's a lot of work, but it turns out that you're going to see when you're programming that like having multiple players is just like a for loop. And ECS handles all of this so wonderfully that it's so easy to do something like this. This one is a special timer and sound effect. Let's see here. Oh yeah, so this one has a sound effect, and it has a cooldown for the weapon. And glowing special bullets and bouncing something. I can't remember what that does. Yeah, so that one's pretty neat. And one more I'll show. Special player controlled bullet. So this one, the right click spawns a bullet that you can move around, and that bullet like moves at a different speed than you, but it interacts with things, and you can do that. So there's so many different things that you can do. It's really cool what people have come up with. So that's going to be like 10%. And just realize that you can come up with whatever you want for your special ability, but it has to have at least this functionality. Alrighty. Enemies in the game. So it's pretty obvious what the enemies are doing, but I have to specify this exactly so that all of your solutions look approximately the same. So enemies will spawn in random locations on the screen every X frames, where X is defined in the configuration file. So I think by default something is spawning once every second. So yeah, I'll look at the config file at the end and we'll play around with that. Enemies must not overlap the sides of the screen at the time of spawn. So when they spawn, they have to be entirely within the screen. Enemy shapes have a random number of vertices between a given minimum and maximum number, which is specified in the config file. Okay, I'll talk about that when we get to the config. Enemy shape radius will be specified in the config file, and enemies will be given a random color upon spawning. Enemies will be given a random speed upon spawning between a minimum and maximum value that's specified in the config file. When an enemy reaches the edge of the window, it should bounce off in the opposite direction with the same speed. And here is going to be the hardest part, but still not that hard because of the way we've implemented things. When large enemies collide with a bullet or a player, they are destroyed, and n small enemies spawn in its place, where n is the number of vertices of the original enemy. Each small enemy must have the same number of vertices and the color of the original enemy. These small entities travel outward at fixed intervals equal to 360 degrees divided by vertices. So for example, if the original enemy had 6 sides, the smaller enemy will travel outward in intervals of 360 divided by 6 equals 60 degrees. Okay? So you can see that when we're playing the game. Let me load that up again. So when I kill a smaller enemy, that one has 7 sides, so its spots go out in intervals of 360 degrees divided by 70. This one is 4, so every 90 degrees there'll be one. This one is 5. This one is like 8, so there'll be 8 of them, etc. Okay, this one is 3, so 120 degrees. So you see how that has to work. So you're going to have to calculate, you're going to have to go to the original entity and figure out how many sides it had from its shape component, figure out its color from its shape component, and then go through a loop and spawn that many entities with a speed and an angle, and we went over all of that math in the previous assignment. The score. So as you saw, up in the top left, there's a score. And the score gets incremented when I kill an enemy. So how does that score work? Each time an enemy spawns, it is given a score component of n times 100, where n is the number of vertices it has. Small enemies get double that value. If a player bullet kills an enemy, the game score is increased by the score component of the enemy that was killed. So if you killed an enemy with 700 score component, you're going to look at that component, the score component, and add it to the current game score. The score should be displayed with the font specified by the config file in the top left corner of the screen. Okay, now we go down to drawing. In the render system, all entities should be given a slow rotation, which makes the game look a little nicer. So if you look at the solution, my player is spinning kind of slowly, and all the enemies are spinning a little bit, and that just makes the game look a little bit more dynamic. Any special effects which do not alter gameplay can be added for up to 5% bonus marks on the assignment. So if you make things flash or the screen shake or stuff like that, you can get up to 5% bonus marks, but just note that your mark can't go over 100, right? But that 5% bonus can overwrite marks that you lost in areas of the assignment. And for people who did the bonus and who made really cool special weapons, I will be showing off the cool bonus stuff and the special weapons in class after the assignments have been submitted. So you will get some time on the stream if that means anything to you. And any entity with a lifespan is current. Okay. We haven't really gotten to lifespan yet, but let me just read this first. So lifespan is going to be a component. And any entity which has a lifespan component, let's say, for example, an entity is given a 100 lifespan. That means that that entity is going to be alive for 100 frames, and then it's going to die. And I'll show you how that's going to work in the code when I get there. But this is just the specification for lifespan. So the big enemies do not have a lifespan component. They just bounce around forever. However, as you can see, the small entities eventually die and they fade out. So they do have a lifespan component. Similarly, the bullets have a lifespan component. And the lifespan just means the number of game frames that that entity is actually alive before it gets destroyed. So, any entity with a lifespan should have its color alpha channel set to a ratio depending on how long it has left to live. For example, if an entity has a 100 frame lifespan and it has been alive for 50 frames, its alpha value should be set to 0.5 times 255. The alpha value should go from 255 when it is first spawned to 0 on the last frame when it's alive. And what that means is that if I look at the bullet shooting here, when the bullet is first spawned, it is completely white. However, over the course of his lifespan, it slowly fades away by changing the alpha channel of its color until the point where it's completely transparent and it dies. So that's what the lifespan is. Also, the P key should pause the game. So if I press P here, just watch. Let me spawn a couple of entities, and I press P, the game should be paused. Okay? So you can see here, I can't move, the game is completely paused, and when I hit P again, the game is unpaused. Okay? And the escape key should close the game. So that's, if I press escape, the game closes. All right, let's go on to the config file. So I've been talking about the configuration file, but here's how it actually works. The configuration file will have one line each. So we'll have a bunch of lines, one line each specifying the window size, the font format, the player, the bullet specification, and the enemy specifications. Line will be given in that order with the following syntax. So let me open up the config file here. It's a pretty short file, so I'm going to put that down on the bottom while I read from this up at the top. So here's the config file that we have, and I'll read this. So the very first line down here, this line, is window WHFLFS. This line is very similar to in assignment 1. However, there's one extra parameter. So this line declares that the SFML window must be constructed with width W and height H, each of which will be integers. FL is the frame limit that the window should be set to, and FS will be an integer which specifies whether the displayed application should be in full screen mode if it's a 1, or not full screen mode if it's a 0. So right here we have 0, which means that it's not in full screen mode. If this is changed to a 1, then it will run in full screen mode. So just keep in mind that I can't. The full screen stuff that I was showing just now that was OBS making it full screen by just blowing it up. But you will actually have to go to the SFML website and see the syntax for how you would make your game in full screen mode. And I can't show you the true full screen mode because my resolution changes and OBS breaks, so I can't do that on screen, unfortunately. The next line here is the font specification. This line defines the font which is to be used to draw text for the program. The format of the line is as follows. So first we have the word font, right? Then we have file. So the second one is the file that the font is in. And so there'll be a directory called fonts, and in that there'll be arial.ttf. Then is the size. So that's the font size. And then the RGB color of the font. So that line is pretty intuitive. Next, we go on to the player specification. This is where things get a little bit interesting. All right. So here's the player specification. First, we have player, and then we have SR. SR is the shape radius of the player. Okay, so down here you can see that the shape radius of the player in the default config is 32. The collision radius, CR, is also an integer, and that is currently set to 32. So the collision radius is where things collide with the player, and the shape radius is how big the player is. So right now they're currently set to 32, so if I run the game, the player is size 32, and the collision radius is also size 32, so whenever you see the edge of the player touch the edge of an enemy, it will die. However, let's change this, for example. so that the player is now radius 128, but the collision radius is still 32. So that means the player is going to be huge, right? But I only collide with the inner 32. So I can sort of go on top of here until I actually touch the inner 32 radius. Similarly, I could have a size of 32, but a radius of 128, in which case, or a collision radius of 128, in which case I will be colliding with stuff way before it actually reaches me, okay? And the reason why we might want to have like different shape and collision radiuses will be explained in assignment 2. But I just want you to see how that works in this assignment and implement that for me. All right. The next integer is speed. So that is a floating point value, and that's a single value, and that is the speed or the number of pixels that the player should travel per frame when it is holding W, A, S, or D. So be careful here, because this is really easy to implement when you're going up, down, left, or right. But when you're holding up and left, you should still travel only 5 speed. Okay? So make sure that you're setting the speed properly when you do that. The next one is the fill color. So here is the fill color of the player. That's in RGB. So that is 555 right now. Let me just change the G component to 255, and you'll see that the fill color, or the internal color of the player, is now green. So that's what that specifies. Let me change that back. Next is the outline color. So right now that's set to RGB, which is red. Okay, I don't need to change that. Next is the outline thickness. So if I set the outline thickness to 1 from 4, you can see that the thickness is very, very small, right? So I've set that down. And the last one is the number of shape vertices. And that is the vertices of the shape. So by default, it's 8. Let's change that to 3. And now look, oh, the player is a triangle. Okay, so that's the number of shape vertices. Perfect. So you'll have to implement all of that under the hood. There is a very similar specification for the enemies, okay? So the first few of these things, up until here, it's the same as the player. So we have the shape radius, the collision radius. However, now we have min and max speed, all right? So we have S min and S max. So if we look down here at the player, we have SR, CR. This is speed min, and this is speed max. So we have a minimum speed of 3 and a maximum speed of 3. Let me just change that to 13. And now we should see enemies spawning with possibly higher speeds. Actually, I don't think I implemented that in the solution. So apologies for that. But this should be every enemy that spawns is going to have a minimum and maximum speed. And I will actually change that before I make the assignment available for download so the solution is correct. All right, so that's what those two are. The next is the outline color. So that is the outline color of the enemy. This is the outline thickness of the enemy. This is the min number of vertices and the max number of vertices. So what that means is whenever you go to spawn an enemy, it will have a random number of vertices between 3 and 8. Okay, and if you can see in here, that all the enemies that spawn are going to have a number of vertices between 3 and 8. So there's a 3, there's a 7, etc. But if I change this 3 to an 8, that means that everything that spawns is going to have 8 vertices. Oh, nope. I didn't implement that correctly. So between 7 and 8, do what I say, not what I do, right? Bad solution. So here we go. Cool. All right, so everything has 7 vertices because I've said between 7 and 8. Next, after this, I'm going to change this back to a 3. This 90, that is the small lifespan. So that means that the lifespan of the small enemies is going to be 90 frames. So if the game is running at 60 frames per second, this means that small enemies are going to last for 1.5 seconds. So let's just have a look at that. If I kill this, yeah, the small enemies are lasting for about 1.5 seconds. You can count that. And second, last but not least is the spawn interval. So at 60 frames per second, the spawn interval of the enemies is 2 seconds if it's 120. So let's change this to 20, and now we should be spawning 3 enemies per second, and my game gets a lot harder. Okay, so that's the spawn interval of the entities. I'm just going to use my special weapon to cheat and do that. Cool. And very last thing is the bullet specification. And the bullet specification is almost identical to the enemy and the other specification. So I won't go over this in detail because you can just read these. Just know that the last thing is L, which is this specification. Okay, so I'm going to go over the code now, and then I'm going to come back and read these assignment hints after I've gone over the code so you can really appreciate what the code is doing. Alrighty. So, oh no, I closed that. That's fine. We'll open it when we come back. So when you get the assignment, you're going to have this source directory. So just like assignment 1. Oh, sorry. Someone had a question out here. How does your player behave when you move it in opposite directions? That is not specified in the file, but for me, I like it to cancel out. So orthogonal directions completely cancel. So right now I'm holding right. Now I'm going to press down left, and I have no movement. So let's say that's what you have to do in the game. Okay, so if I hold all the keys, it's not moving. If I hold opposite keys, it's not moving. It's a good question. Someone said the player, his name is Phil because it's Phil's color. That's pretty good. I like that. Okie doke. So you'll get these files in the assignment. So let's go over each of those. The first one is Common.h. So Common.h is just going to be included by everything, and this is sort of a standard practice, is if a bunch of your files are going to be including the same stuff, well, why not put it all in one header file and then include that header file in multiple files? So here we can see that we've included some graphics stuff, some file stream stuff, some memory stuff, our vec2.h, and we've also got a type def here, or we've got a using here, which says using PTR equals standard shared pointer T. And so what this does, oh sorry, I should make that a bit bigger, is it just means that we've specified that wherever I say PTR T, that is equivalent to saying standard shared pointer T. So it's just a shorthand version so that if you want to, you don't have to type standard shared pointer all over the place. So we're using PTR equals that, right? So that's what I've that's what I've set up for you. Next, let's look at the components. So the components are each individual classes that hold data, all right? So this data here, so for example, we've got the transform component, and I've called that C transform. So transform C is component. And just as we described in the slides, these components are pure data. And we're going to use these components and attach them to entities in order to get our behavior. And so I know that, like, you know, as we're going through this lecture, this may seem like a lot of information. And like, oh, we've got all this stuff going on at once, like 5 different classes. Trust me, when you actually start sitting down and looking at this, it's not going to seem as bad. And by the time we get to assignment 3, you'll be so used to this, you'll wonder how you ever programmed a game using any other type of system, okay? So I understand if it's a little bit overwhelming at first, but just follow along and then come back and watch the parts that maybe you didn't understand the first time around. So the transform component is going to have 3 members. It's going to have a position, it's going to have a velocity, and it's going to have an angle. And just keep in mind for this assignment, position indicates the position of the center of the object, okay? So it's going to be the center of the bullet, it's going to be the center of the player, it's going to be the center of the enemy. Let me really quickly bring up so next let me do this first. So this is the shape component. Now, every single entity in our game is going to have a circle shape component. And now I actually do have to bring up my Blackboard, and I forgot to get that ready, so bear with me for a second. Oh, there's my blackboard behind the scenes. All right, so we're going to the blackboard. Every single... Oh, why is this still not working properly? Okay, perfect. Got it. So every single shape in our game will be a circle shape. All right? But you may say, but sir, but Dave, we just saw that there were triangles. There were heptagons. There were squares. Everything is not a circle. Well, it turns out SFML is going to let us draw all of those regular polygons very, very easily. How? Well, let's look quickly back here. When we construct our shape component, we're going to take in a number of parameters. So the shape is going to have a radius, it's going to have a number of points, it's going to have a fill color, it's going to have an outline color, and it's going to have a thickness. So the first thing we did there was say that it's going to have a radius. So the radius, of course, of a circle is just this. It's the distance from the middle of the circle to the outside of the circle. The next parameter is the number of points. So in computer graphics, whenever you want to draw a circle, you can't actually draw a circle. Because if you think of what a circle is, you are drawing a circle is an infinite set of points. It's the set of points which are exactly our distance away from the circle. So like if I zoom in here on my blackboard and look at how MS Paint drew this circle, well, it's actually a bunch of different number of pixels, right? Maybe I can keep zooming as this is the max zoom. But you can see here that this is not a true circle, right? It's just drawing a bunch of pixels, a finite number of pixels where it thinks it should be. It turns out there's another way that we could draw a circle. We can define a number of points. So the way SFML works is that we're going to have a center point to our circle. And then let's say we've set up a number of points, and that number of points is going to be equal to 4. So what it does is it spaces out those 4 points equidistant on the circle, and then it draws lines between those points. Okay, so here's the first one, here's the second one, here's the third one, and here's the fourth one. So if you specify, hey, SFML, draw me a circle with 4 points, that means you're drawing something with 4 sides. Okay, so the number of points is equivalent to the number of sides. And so here you've got 4 points, 4 sides, so you're effectively drawing a square. And what happens is, if you gradually increase the number of points here, right, you can see that you start to approach the approximate shape of a circle. So if I put in draw me a circle with like 64 points, it's going to look like a circle on the screen, even though it's a 64gon when it actually draws it, all right? So we can exploit this part of SFML, which draws circles via a certain number of sides, in order to really easily draw the number of sides for our game. And it turns out I've already written the code to do that for you. So let's go back to there. Alrighty. So first of all, the circle is an SF circle shape, and you should be familiar with those by now. So all I do is I say circle.fillColor with the fill color that I passed in, circle.setOutlineColor with the outline that I passed in. The circle was constructed, so the constructor of the circle takes in the radius and the number of points. Then I set the outline thickness, which is the thickness over here. And then I do one more thing, and it's the following. By default, in SFML, if I can go back to the blackboard, okay, let me erase these things. By default, the position of a circle, as you saw in assignment 1, is, I wanted to draw a square here. The position of a circle is actually the top left position of the bounding box that contains that circle. So if I say, hey, circle shape, take this position, it's the top left up here that's being positioned. But I actually want for this assignment, since everything is a circle, it makes far more sense to position the circle on the center, right? So I want the position of the circle to denote the center of the circle. So what we have to do is tell SFML, whenever we set up a circle shape, I want to set an origin, okay? So by default, the origin of a circle is up here in the top left corner. If I want to translate the origin to the middle so that it's drawing it where I think it should be drawing, what I do is I can call the setOrigin function. And if I go back here to the drawing, if I say setOrigin with an X and a Y value, okay, it will set so that that X and that Y, that is where the position of the top left of the object lies, okay? So that's where the position of the object lies. So it's a relative distance, as someone just said, in comparison to the top left corner of the object. So if I want the origin to be the middle, all I have to do is set origin R in the X direction and R in the Y direction, okay? And then SFML thinks that the position is in the center of the circle. So when it goes to draw the circle, it's drawing it with the center at the position and not the top left at the position. Okay, so let's look how we do that. Well, it's really simple. All I have to do is say circle.setOrigin radius in the X direction and radius in the Y direction. And so whenever I draw this circle shape, it's going to draw it such that its position, or the position of the transform, right, is in the middle of the circle. And so I know I said before that components are pure data, and here we have some code in the component. Well, I'm trying to set it so that, okay, you can set values in the component, but we're not actually doing any logic like collision logic or movement logic or anything like that in the component. This is all just constructor stuff and setting the properties of the internal SF circle shape. So we're allowed to do that. All right. The next component is the collision component, because you've got to have a collision component, right, if you want things to collide. And so the collision component, since everything in our game is just a circle, then we're going to just need a radius for the collision component. So the collision component as a input parameter to the constructor takes in a radius, and we just set the internal radius value. So that's pretty easy. The score component is again very similar to the collision component, whereas it just stores one value. So here we're going to pass in a value for the score, and it's going to set that internal value. So whenever you go and you construct an enemy, you're going to give it a score value equal to the number of sides times 100, right? Here is the lifespan component, and I'm actually going to change this live, and it will make your life a little bit. No, okay, I know why I have this now. Apologies. Lifespan is going to change, is going to stay like this. So the lifespan component is going to have two variables. One. No, I'm going to change this. Here we go. All right. I'm going to change this right now. So this will be easier for you. And I just realized why this will be easier for you. All right, so this is remain, and total. Perfect. So here, the lifespan is going to have two values. This is the amount of lifespan remaining on the entity. And this is going to be the total initial amount of lifespan. All right, so what does this mean? It means that, let's say, for example, we're going to have an entity that has 100 total lifespan. But let's say it's been alive for 30 frames, okay? So if an entity has 100 total lifespan, this value is going to be 100, and if it's alive for 30 frames, then this is going to have 70 lifespan remaining. So essentially what you're going to do in your lifespan system is you're just going to read the lifespan component of an entity, and you're going to subtract 1 from the remaining amount of time. And then when that value hits 0, well, then your lifespan is, that's it. You destruct that entity, right? So that's what that does. Okie doke. Now, you're also going to have an input component. So this input component, you're going to attach to the player. And what this does is it currently just holds whether or not a current input button is being pressed, okay? So it's going to, the input component is going to record whether or not the up key, the left key, the right key, the down key, or the shoot key was pressed. And then what you're going to do in your movement system is you're just going to see, say, you're right. So let me finish this first. Your movement keys are any entity which has an input component attached to it is going to be controlled by the input keys. All right. So you can create a second player that's controlled by input keys just by attaching an input component to it. You could also have a special weapon that lets you take control of enemies if you want by attaching input components to it. This is going to be really cool. Someone in the chat just made me realize that I no longer need this, okay? We don't need to pass in how much time is remaining. We just need to pass in the total amount of time, because the remaining amount of time is going to be equal to the total amount of time when we initialize this object. So if I passed in 100 for the total amount of time, well then initially there'll be 100 remaining, okay? So that's what lifespan does. Okie doke. Now what we're going to do is we are going to move on to another file. So those are the components. Now let's look at the entity class. So the entity class is exactly what we described in our slides. So it's going to have 3 of these values. It's going to have the private member variables of whether or not it's currently active. Initially, that's going to be true. It's going to have the ID, so that's the unique integer identifier associated with this entity. By default, that's 0. And it's going to have a tag, and we give it some default value. We're going to have the public pointers or shared pointers to transforms. We're going to have this entity constructor. Oops. That is supposed to be a private constructor. It's a private constructor so that we can't accidentally create any entities on our own. So it's good that I went over this in class. And then we're going to have the access functions to the private member variables, right? So we're going to have isActive, which reads from active. You're going to be able to get the tag. You're going to be able to get the ID. And you're also going to be able to destroy the object by calling destroy. So over here, let's have a look at these values. Well, these functions are pretty simple, right? All it's doing is storing some data and getting that data. So the only real interesting thing here is destroy, and destroy just sets mActive equal to false. That's it. Okie doke. Now let's look at the vec2 class. So the vec2 class is what we talked about in class last time. And we're going to have a default constructor, a constructor with some inputs. We're going to have equals and not equals operators. We're going to have all of our basic arithmetic and plus equals arithmetic and arithmetic equals functionality. And we're also going to have a distance function. So keep in mind that you have to implement the vec2 class for this assignment. And I don't think, did I actually put that in the README file anywhere? Okay, so it's in the marking scheme. But just realize you have to implement all of this functionality for vec2. That should only take you a few minutes, right? It's just the addition and subtraction and multiplication, etc. So you have to do that because right now, all of these operators are just returning 0. So you'll very quickly realize that your program won't work until you go and implement this. Okay, so that's vec2. You have to implement that as well. Now let's look at the Entity Manager class. And the Entity Manager class is exactly what we said it was in the last class. This is copied straight from the slides. So we've got the Entity Manager class. It's going to have several private variables. This should be equal to 0 initially. So we've got the vector of entities, which is all the entities. We've got the vector of entities, which is the entities we want to add on the next frame. We've got the entity map, which is going to map strings to entity vectors. So that's the tag to the vector holding all the entities with that tag. And then we've got the total number of entities so that we can assign a unique integer identifier to things. And if any of what I said just then confused you, you need to go back to the previous lecture where I explained all of those variables in detail, okay? We're also going to have a function called remove dead entities, and that's going to be a function which we're going to pass it in a reference to a vector, and it's going to iterate through that vector and remove all of the entities from that vector where isActive is false, okay? Down here, the public-facing side of things, we're going to have an entity manager constructor. We're going to have an update function, and I'll show you what that does in a second. We're going to have the ability to add an entity to the entity manager, which will return a shared pointer to that entity. We're going to be able to get entities, all the entities, and we're also going to be able to get the entities of a specific tag. Okay, so let's go over and look. You're going to have to implement some of this functionality, and which of this functionality is here in inside Entity Manager. And if you're at this point and you're sort of confused in what to do first when you open up the assignment, I have a list of the order of operations you should go through when you do this assignment. So Entity Manager, I can remove this now. The constructor really does nothing. So the update function is what you are going to have to implement for this assignment in the Entity Manager. Now, I basically gave you the code for this in the last lecture, okay? So if you look in the slides, a lot of the code for this is just there. So to do, anywhere you see to do, that's what you have to do as a student in the class. So what you have to do first is add the entities from the mEntities2add vector to the proper locations, meaning you add them to the vector of all entities, and you also add them to the vector inside the map with the tag as a key. So I went over that again in the last lecture. And then what you have to do is you have to remove all of the dead entities from all of the vectors. So the first thing you do is you remove the dead entities from the vector of all entities, and then you have to go through the map and iterate over each tag in the map and remove each of those tags vectors in that way, okay? So that map we explained last time. So for example, you're going to have like a vector of enemies, a vector of bullets, and you have to go through and remove those. Now, a neat way of iterating through a map in C++, this is a cool syntax for that. So it says, here's how we iterate through the key value of a map, okay? So we say auto-reference the tag and entity vectors, so we can assign values here, or variables to that. In the entity map, we are going to remove the dead entities from each of the entity vectors. So all this does is it iterates through the map for you and passes each of those entity vectors that are inside the map into the remove dead entities function. So all you have to do for this assignment to remove the dead entities is implement this function, okay? So you have to implement the function which looks through each entity in the entity vector, calls isActive, and if isActive is false, then you remove that entity from the vector. Now keep in mind, you're going to have to do something to like, you know, avoid iterator invalidation while you're doing that. But feel free to like look online and Google how to remove things from vectors as you're iterating them, or how to remove all things from a vector while you're doing this, okay? Okay. So now we go down to add entity. You have to do some things inside the add entity function, inside the add entity function. So implement this function so that entities are added to the Entities2add vector, and then added to the proper locations in the update function later. So we're going to create the entity shared pointer. So we've got auto entity equals standard shared pointer entity, new entity, and do I actually have this? One second. There's the ID that's being passed in and a tag that's being passed in. This shouldn't be a reference to a data type like that. There we go. Okay, and this shouldn't be returning a reference. That should be pure data. So excuse me for editing this live. So we're back to the Entity Manager, and what's this saying? Okay, so the other thing we need to do over here is because we have a private constructor, we have to say that entity has a friend class Entity Manager. So that means that Entity Manager can construct entities, but nobody else can actually construct entities. So now that error goes away. Create the entity shared pointer. Now, I explained this a bit in the last lecture. Leave this line as it is, okay? You are just changing this line. So this is going to add it directly to... You know what? Screw this. You don't have to do this function. Why am I making you do this like trivial change? I'm just going to do it for you. M entities to add dot pushback entity. That's such a trivial, stupid thing for me to confuse you with. So that function is completed for you. You don't have to do anything in add entity. I apologize. My last year's self was being very petty. All right. Down here in get entities, this is properly returning the vector of all entities. However, there's one more function left that you have to implement, which is right now, this wants to look into the map indexed by the tag that we're passing in and return the vector of all entities based on that. And so this is incorrect. You're going to have to do something here to get the proper vector from the entity map. Okay, so this I do want you to do because I want you to have a little bit of knowledge working with those maps. All right, so that's what you have to do in Entity Manager is implement the update function to actually take the things that we wanted to remove and add on the last frame and do that removal. You have to implement the remove dead entities function, and you have to implement the get entities with a tag function. Cool. Now, all of that really shouldn't take a lot of time. It probably takes more time to explain than it does to implement. Last but not least, certainly not least, is the game class, okay? So the game class is going to contain all of our actual gameplay logic for the game. So what is all this stuff then? Up here, what I have done for you, if we can reopen the config file quickly, let me go back. Assignment 2. All right. So, or let me open the README file. So this is the README file. And you can see in the README file that down here, the specification of the player, the enemy, and the bullets have all of these variables. What I've done for you here is I've just created structures that contain all of those variables. So for example, enemy, you have enemy config up here, right? And that just contains all the variables. So you don't need to sit there and type all of those variables manually. So inside the game class, I have created player config, enemy config, and bullet config structures, and you can read directly into those structures. And I'll show you how to do that once we get to the actual code. So that's what those things are, is the game class is going to hold objects to store all of those config variables that are in the config file. All right. What else is here in the game class? Well, first and foremost is the window. We've got to have a window that we're drawing to, right? So we've got to store that window class. The game also stores the entities. So that's the Entity Manager. So the Entity Manager instance is called mEntities, and whenever we want to use the Entity Manager, we'll be referring to that variable name. Next, we have the font and the text element that will be drawn to the screen. Then we have the score, the current frame, the last enemy spawn time. Maybe that's something you're going to need, because remember, there's an interval to each enemy spawn time, so I've created that variable for you. I've also got a Boolean whether or not the game is being paused and whether or not the game is currently running. And I've also got a separate variable here for the player. So you can store a reference to the player if you want, because it's pretty slow to always go get the player from the entity manager. So if you want to store a separate reference to the player in this variable, you can. Okay? Just should I even do that? Yes. Okay. We're gonna allow you to do that in this assignment. In the next assignment, I'll show you the better way of doing this. So you can see already how such a simple game in concept, right? There's a lot of stuff going on here. But what we're doing is we're building the engine for this simple game that we will use later to have more complex games. All right? So trust me that this is going somewhere. All right. Next, we have an init function that's going to initialize the game state based on the config file. So we're going to pass in the file name of the config file here, and the init function is going to read everything in. There's a set paused function, and you'll use that to pause or unpause the game. Then we have all of our systems. So this is the movement, input, lifespan, rendering, spawning, and collision systems. And then we're going to have some helper functions here for us that you're going to implement in order to do things like spawn the player, spawn the enemies, spawn the small entities. And I'm going to show you what each of those functions does and how to implement those. Lastly, we have very, very few public-facing functions in this game class. We're just going to have a game constructor, which takes in the config file, and then we're going to have a run variable. So if we look over in main.cpp, here's how we actually launch and run our game. It's just going to be game G. So this is the variable name G. It's going to take in config.txt, and then we just run it. All right? Someone's asking, is it a bad idea to read the config file in the constructor? There are religious debates about that. I'm not going to get into it. I'm just going to say we're doing it the way we're doing it in this course. In an actual game, you may not want to do things that can throw exceptions inside constructors. But we're not going that deep with C++ in this course. All right, so that is the header file for game. Now we're going to go into the implementation file for the game. So again, real quickly, we have our header file, which is our declarations. I should have said this before. And then our CPP file, which is our actual implementations. So let's go over to the game implementation file, the CPP file, and we'll go through this. So inside our game's constructor, we call init, okay? So inside the init function, we're going to do several things. The first thing is the thing that you have to do, which is read in all of the configuration variables from the config file, okay? So here's the config file again. You are going to read in all of the variables from the config file in here. So let me start you off with that, and let me do an example of reading in the player, okay? So let's say that we've got our standard if stream fin based on path, okay? So that's the config file. Remember, we did this in assignment 1. We set up an input stream. I'm going to include fstream, or have I already done that? I think we've already done that. Yeah, we have already done that. All right, so Game.h includes Common.h, and Common.h includes fstream. That's how we're able to use that here. See how that works? All right, so just to get you started with the input here, or the init, what's going to happen is, let's say that we are currently at the player reading part of the file. All right, we have this mPlayerConfig variable. That variable has all of these player configure options in there. So what we're going to do is we're going to read in all of the different options from this into those variables. So what we do is we come over to the README. I'm going to look at the player variables. Okay. Let me see if I can do this here. I'm going to put this like this, and I'm going to do this here. So fin, oh geez, this isn't wide enough, is it? Not really. So many windows open. So here's our player specification. Here's our code. Let me really quickly do this so you have a bit more room. So I can say something like, when I get to that line of the file, I can say fin. What's the first thing? Well, it's going to be mplayerconfig.sr. Then I can read in mplayerconfig.cr. Then I'm reading in mplayerconfig.s, right? So you can store all of these variables inside this player config struct that I've given you. All right, so that's why I've put it there, so that you can store all of these many variables inside here, and then later on when you go to spawn enemies or spawn the player or give them properties, you can read from the player configuration structure that I gave you. All right, but keep in mind up here, you've also got to do things like read in the window size. And down here, you've got to set the window size based on the parameters that you read in. Excuse me. Similarly, you're going to have to set the frame limit of the game equal to what you said, what I put in, and also whether or not this is full screen mode. So once we've read in the init, the config file, and once we have initialized the window, we're going to spawn the player. Okay? So spawn player is down here somewhere. And what I've done for you here is I have created a sample spawn player function so that you can get started with this. And when you go to spawn enemies, you can use this template code to actually spawn enemies as well. So what is the player going to have? Well, first of all, to do, you want to finish adding all the properties of the player with the correct value from the config. So the first thing we're going to do is we're going to say, hey, Entity Manager, we want to add an entity. And we want to add an entity called player, right? So we give the player tag to the Entity Manager. So the Entity Manager is going to add this all behind the scenes and return us a standard shared pointer to an entity that has the tag of player. So this is all you ever need to worry about. This is why we're using a factory pattern, okay? Because in order to add a new entity, all we do is call on our Entity Manager. Super simple. And it's all that data is all taken care of us. We don't need to worry about that at all. So that's amazing. And you'll see like how useful that is when you go to program. Next, we are going to give this a transform. Okay. Now, what you have to do in the assignment is give this a transform so that it's at the middle of the screen, right? But what I'm doing here is I'm just giving it a transform with 200, 200, and a speed of 1, 1. So if we go over here to the transform component, we can see what the input parameters are. That is the position, the velocity, and the speed, or the angle. So over here in game, I'm passing in the position, the velocity, and the angle. All right, and we use standard make shared C transform in order to set the transform. So we're just saying, hey, the transform is currently null. I want to put a transform on this. So all we have to do is give the entity a transform. Next, we're going to give it a shape. This shape is going to have a radius of 32. It's going to have 8 sides. It's going to be a dark gray color fill, and it's going to have a red outline and a thickness of 4. And of course, when you go to actually implement this function, you're not passing in all these hard-coded values. You are reading from the player config structure that you read all the config variables into. All right. Someone asked why we're using standard make shared. Standard make shared is the preferred way of creating shared pointers. And I explained that in a previous lecture. So we're using standard convention and safety. Here we are going to give the player an input component. And down here, we are going to set our internal player variable to this entity. Okay? So we just have an additional variable living outside of the Entity Manager class so that we can easily get access to the player. Okay. Next function would be run. So run here is the main loop of the entire game. So remember, in Game.cpp, what we do, or sorry, in main.cpp, all we do is call the game's run function. So in game run, this basically just says, well, the game has an internal variable called running, which is set to true. And then while the game is running, we do all of the things that we want to do, right? So just like we saw in the slides, it's going to update the entity manager. It's going to call the enemy spawning system. It's going to call the movement system, the collision system, the user input system, and the render system. And then maybe we want to increment the game frame so that we can implement some other functionality. But what you have to do here is implement the pausing functionality, okay? So here, when I run the game, let me wait for an enemy to spawn, and I hit pause, you can see that some things are still happening, right? The player is still spinning, and it's still being drawn, it's still being animated, but there's nothing spawning. So what you want to do here is when you come over, you look, there's a paused variable. So you want to say, okay, if m paused, do something. So which systems do you want to run while the game is paused, right? So you can do something like this. Maybe you don't want the movement system running if the game is paused. So maybe you could say if not paused. That's a better way of doing it, right? So if the game isn't paused, then we want the enemy spawner and the movement. But maybe we don't want collision, we don't want user input, we do want rendering. So this is what you'll do for that in order to implement paused functionality, okay? So that's an easy way to implement your pausing, is that you turn off certain things. All right. Someone said, should we worry about the current frame exceeding a big value? No, we shouldn't. Well, the current frame is an integer. If you are running this game at 60 frames per second for 2 billion frames, tell me how many years is that, okay? So the answer is no. You don't need to worry about that. Here is the function that you have to do that implements whether or not the game is paused. That's really easy. You just set the Boolean variable. We talked about spawn player here already. Here is the spawn enemy function. So you have to write this function. So you have to make sure that an enemy is spawned properly with the menemy_config variables, and the enemy must be spawned completely within the bounds of the window. And here you are spawning an enemy with a random position within the bounds of the window, completely within. So the enemy's edges can't overlap, okay? And we talked about how to create random numbers in a given range in the last lecture, and that's why, because we will be using that for this system. Then we're going to have a function which is spawn small enemies. So in here, we're going to spawn small enemies, and this function takes in an entity, okay? So whenever we kill an entity, we can see that, like, for example, this blue septagon, it's going to spawn 7 blue septagons. So whenever we spawn small enemies, we're going to, before we kill the big entity, we're going to pass that entity as the input entity to this function. And the reason we do that is because we need to be able to read the properties of that larger entity to create the properties of the smaller entity, all right? So when we create the smaller entity, or enemy, we have to read the values of the original enemy, and that's the E here. So we're going to spawn a number of small enemies equal to the vertices of the original enemy. So how would we get the vertices of the original enemy? Well, we could do something like this. We could say int vertices equals, so E is going to have a C shape, okay, because it has a shape transform. Let me make this just a little bit bigger. So it's going to have a C shape variable. That C shape variable has a circle inside its component. So we look over here at components. We see the shape component. Inside that, it has a circle, okay? So the circle is an SF circle shape. So over here we have E, C shape, circle, and then we can say get point count. So get point count is the function from the SFML circle that allows us to get access to that. So then you would say something like the following. For int I equals 0, I less than vertices, I plus, in here now, we would say auto enemy, or maybe small enemy equals m entities dot add entity. So we're telling the entity manager to add an entity, and maybe we call this small, right? So we're going to give it a tag of small entity. And that's because we want to do things to small entities that we don't do to larger entities or larger enemies. And then we would like add all of the different properties of this small enemy. So we're going to set each small enemy as the same color as the original, but half the size. So up here, you could read properties like E, C shape, circle, dot get fill color. The fill color is the fill color of the parent should be the fill color of the small one, right? So that's how you do that. You read the properties of the original one and set them equal to smaller one. And remember that the small enemies are worth double the points of the original enemy. So you could say something like E. Now we want to add, or small enemy, we want to say that C score equals standard make shared C score. And what score do we want to give it? We want to give it E's C score variable, right? Times 2. So I've given you one of these lines here as a solution. So people who watch this actually get stuff for them. But here's how we do things like add components to things and give them values. All right. I know it's like someone out there said it's like I've done the assignment for you already. So that's what you have to do for the spawn small enemies function is read the point count of the parent or the bigger enemy that was killed, and then create a for loop that spawns that many enemies, figures out all the stuff. All right. So that's the spawning of the small enemies. Next is the spawning of a bullet. Okay. So to do, implement the spawning of a bullet which travels toward the target. The bullet speed is given as a scalar speed. You must set the velocity by using the formula that I said in the notes, okay? So let me go over what that means. Let me go back to the blackboard. All right, so let's delete all this stuff from the blackboard. At some point, you're going to have this assignment working to the point where you start mouse clicking, right? So let's say that this is my player, and up here in red, oh, that's bad for colorblind people. So up here in blue, let's say that is the mouse position, right? So I've got the player's position. So the P position here down here, that's X and Y. And up here, I've got the mouse position of X and Y. So what I've done is I've given you a scalar speed S. So that speed S is how many pixels per frame you should be adding to the position of the bullet once it's spawned, right? So that means I want the bullet to travel this many pixels per frame, this diagonal, usually it's going to be a diagonal, right? That is the hypotenuse of a right triangle, which points from the player to the mouse position. All right? So how you do that, how you figure out this X, this DX, and this DY value, I went over that at length in the notes last time with the math stuff, okay? So you're going to have to figure out that. That gets set to the velocity, and then the velocity gets added later on. So that's what that is. And that's basically the spawning of a bullet. And remember that you have to bring in all of the bullet config stuff that you read in from the config file. Okie doke. Next is spawn special weapon. And spawn special weapon here takes in the entity that spawned the special weapon. So if this is the special weapon being spawned by the player, then you would pass player into here, okay? And then the special weapon might need to be fired from the location of the player. Oops, and I forgot to say that spawn bullet takes in two variables. This here is the entity that's shooting the bullet, so typically that's going to be the player. And here is the target that it wants to shoot toward. So this target is going to be the mouse position for standard firing of bullets. And similarly, spawn special weapon, here is where you're going to put in all of your code for actually spawning a special weapon. All right. Now we get to some of the systems. Perfect. So the first system, and the most important system probably, is the movement system. So what you want to do is, in order to move your player, you're going to read in the mPlayer's C input component to determine if the player is moving or not. So how do you do that? Well, you can say if mPlayer, because that's pointing to the player. We got a special thing for the player. C input component, and then we're going to read in left. So this says, is the left key currently being held down by the player? So here's how I recommend you implement this, okay? Because you don't want to do things like determining whether left and right are held at the same time, or up and down, or up and left. You don't want to have like all possible input key combinations there. So here's what I recommend. It's actually quite simple. So let's create a vec2, and this is going to be player velocity, right? And that initially gets set up as 0, 0. So I can pass that in if I want, but by default, it's also 0, 0. So here we have a player velocity. Now, if the player is holding left, okay, then what do we want to do to the player's velocity? Well, we want to make it go to the left. How does it go to the left? Well, we can say that player velocity dot x minus equals m player config dot s. So what does that mean? It means that when we're holding the left key, I want to go negative, so the minus, in the player's x direction of the speed that I want the player to go. Right? Pretty simple. Similarly, else, or not else, because we can hold multiple things, right? So if it's player right, then I want to have the player's x velocity is going to be adding the speed. All right? Okay, so you see how this works here? If we're going to set up a new player velocity every frame, that's initially going to be 0. Then we're going to read in the inputs that are currently being held by that player. So we're going to subtract if they want to go left. We're going to add if they're going to go right. And look what happens. For free, if the player has both left and right being held down, it's subtracting the speed here and adding it back here, so the overall velocity is 0. Okay, so that's what we get for free from that. All right, and you can do the same thing for up, down as well. So that's the player velocity. And then what you would do is, after you've calculated what velocity the player should have, you can say m player c transform, right? Because that's the transform. And then you want to get the velocity is equal to player velocity. So that's how you set the player velocity of the player based on the input values. Really, really simple. So that's how our entire input system works. The only thing that's missing here is how we actually set the values of these input values, but that's handled in the input system. It's not handled in the movement system, right? So see how we're separating our code here? Like, whether or not the player is currently moving left should have nothing to do with the key that's bound to move left, right? Like the movement system doesn't need to know anything about the W, A, S, or D keys. We want to keep that functionality completely separate. All right, so that's what we do there. And then once that is done, in order to update the movement of the player, we just say that the player's position, so we go player transform position.x, we add the velocity.x. And we have the player's position.y, it gets added the player's velocity.y. Now, the reason I'm doing the component-wise addition here is because I haven't implemented the vec2 class. So once you implement the vec2 class, you'll be able to say the following. M player transform pos plus equals M player transform velocity. Done. And what this does is it updates the player for everything. Now, keep in mind that all we're doing here is, for an example, I'm only doing this for the player. When in actual fact, what you want to do is do this for all entities. So all you have to do for that is you say for auto E in M entities dot get entities. So look at that. So if you want to do this to every single entity, all you have to do is just say E and E. And so this one for loop with one line of code updates all the velocities, updates all the positions of all the entities in the game. So this is essentially what you're going to be doing, and I just kind of done that for you. But you're gonna have to do that for yourself, so I won't leave it up on the screen for too long. You know, you can't pause or whatever. All right. The next thing is the lifespan lifespan system. Okie doke. So to implement all of the lifespan functionality. So here is the functionality that you have for your lifespan. And essentially, all you have to do, and I'm going to add a line here, if entity has greater than 0 current lifespan, subtract 1. So what does that mean? So for every entity, well, I'm also going to say this. If entity has no lifespan component, skip it. So for each entity, the first thing we're going to check is whether or not it has a lifespan component. Because remember, we're only putting lifespan components on things that we want to die after a certain amount of time. So for example, the player has no lifespan component. And since it has no lifespan component, we don't want to actually look at it. So what we could do here, again, just to show you, is I can say, let me just go up here, for auto E in M entities dot get entities, if not E lifespan, continue. Why? Because remember, by default, in our entity class, we have a bunch of null pointers to these transforms. So if we have not specifically added a lifespan component to our entity, then this will be null or 0. So E lifespan will be null or 0. So I can say if it doesn't have a lifespan component, if it hasn't been set up yet, continue. Because I don't want to do anything to components in here, or to entities in here that don't have a lifespan component. All right, so that's what we do. Then you would say, inside this for loop, now let me just, I'll remove this because I've got the pseudocode down here. If the entity has a lifespan component and it currently has greater than 1 lifespan, subtract 1 from it, right? Because the current lifespan, or the remaining lifespan, let me go that remaining. The remaining lifespan is how many frames it has left to live. So if you just subtract 1 from it, that's it, you're done. So after you've subtracted 1, if it has lifespan remaining, so if it has greater than 0 lifespan and it's alive, you want to scale its alpha channel properly. So how do you scale the alpha channel of an entity? Well, let's just say we want to scale, for example, the player's alpha channel. All right. So the player, it has a C shape component. That shape has a circle, and that circle has a fill color, right? So I'm going to say auto color equals this. Okay. Now, how do I scale just the alpha channel? Well, color is going to have R, G, B, and A. So it's going to have red. It's going to have G for green. It's going to have its B, and it's going to have color.a. So what you can do here is read in the values of the previous color and then create a new color and set the color of that thing. So let's say I'm going to have int new alpha equals, let's say it's just 100 and 100, right? And now I want to set that. Well, what I can do is now I've got a copy of the color here. So I can say SF color, new color, and that is going to be color.r, color.g, color.b, and then new alpha. Then I take this again, the circle, and I set the fill color equal to the new color. All right, so that's how I would do that, is when I've calculated that new alpha. That's how I set the color, or set the alpha channel, is by keeping the RGB of the previous color the same, but just changing the new alpha color. So if it's still alive and it has a lifespan, we have to change the alpha. And if it has lifespan and the time is up, then we just destroy the entity. So if our entity is E, we just call E destroy. Now, when we call destroy, remember, nothing happens right away. On the next frame, the entity manager is going to clean up that entity for us. All right, next is the circle collisions. And the circle collisions, well, there are going to be some collisions that you have to do in here. One of those is going to be, for example, the collisions between the player and the enemy, right? And so the way you can do that is you can say for auto E in M entities .get entities player. So here you're looping over all the players, or so let's call this P, okay? And then we say for auto E in M entities .get entities enemy, if that's the tag that you've given to them. So now what you're doing is you've looped over all the players, and for each player, you're looping over all the enemies. And so now you can do something that says if there's a collision between P and E, destroy the player, destroy the enemy, and respawn the player. Okay? And again, P is going to have a C collision component. That's going to have a radius. So what you're going to have to do is you're going to have to go through the last set of slides where I told you how to compute circle-circle collisions. And you're going to have the collision radius. The transform component is going to have the position. And so if the distance between one entity and another entity is less than the sum of the radiuses, that's when you have a collision. So you could do something like this. You can say float dist equals P C transform. So in the transform, there's a position. A position is a vec2. And if we look over here, vec2 is going to have a function called dist that you've created. So then you can call .dist, and you can pass into there another vec2, which is the enemy's C transform position. So now you've got the distance between the player and the enemy. And then you can get the radius of the collisions of both the player and the enemy, and you can do the math to see if they both collide. Then what you have to do is you have to do the exact same thing, except you have to say for each bullet, right? So for each bullet and each enemy, you want to do the same sort of calculation. And the last thing you want to do down here is the same thing you did in assignment 1, whereas you have to make sure that enemies bounce off walls, and you have to make sure that the player can't leave the bounds. But you see how we've put all of the collision stuff inside our collision system, and none of the other systems know about that. Down here, you can, this is where you're going to spawn the enemies. So you're going to read the current frame, subtract the last enemy spawn time to see how long it's been since the last enemy spawned, then read in the value from the config and see how much, okay, just someone in the chat said, please, you are getting time. Nobody ever posts the Discord in here, okay? Nobody ever posts Discord information in the Twitch chat. The Discord is for students only. If you're listening to this, I'm sorry that I had to time you out, but I can't have the Discord link in public. If you need the Discord link, send me an email, and if you're a student in the class, so if your email is from @mon.ca, I will send you the Discord link. So please do not post private information for the course in public. All right. So this is the enemy spawning stuff. That's there for you. You implement this function. And last but not least, what I've done is I've just drawn the player. So in order to draw things, what you have to do is you first clear the window. Actually, let me compile, because I don't think this is even going to compile, because I made a few changes here. Let me see if this is compiling. Oh, wow, it'll compile. So let's see what happens when I run this. When I run it, all we have is a player that spawns at position 200, 200, and has a specific velocity. So what did I set that up as in the sample code? So by default, the spawn player spawns the player at 200, 200, and it has a velocity of 1. And 1 in the X and 1 in the Y. And since we're running at 60 frames per second, this means that this is moving downright at a speed of 1 frame or 60 pixels per second in the X and the Y. So down here in the rendering system, what I've done is I've given you sample rendering code for just the player. So what happens to draw the player, we're going to set the circle shape's position to the position of the transform of the player. Then we're going to increase the angle of the circle in order to, so we set the rotation equal to this angle, and that setting of the rotation, increasing the angle and setting the rotation, is what gives us the spinning effect. Then what we do is we tell the window to draw the shape of the circle. Okay? And then we display. So what this says is that all you have to do here is you have to change this from only drawing the player to drawing all the entities. All right? So you have to do that for each entity, but that's just as simple as creating a for loop. All right. And the very last thing that we have to do, I know that this has been long, but again, I'm going over this as sort of a tutorial, right? We had the lecture part that explained the assignment, and this is like a bonus free tutorial for the whole assignment, okay? So that's why it's long. So here is where you're going to handle user input. So handle user input here. Note that you should only be setting the player's input component variables here. You do not implement the player's movement logic here. The movement system will read the variables that you set in this function. So 1 second, I'm just going to take a little sip. All right. So the way we're going to do the event system is that we've got this SF event, we poll the event, and then we have this event object, and we can query what type of event it was. So if this is the closed event, then we're going to close the window. And in order to close the window, we just set mRunning to false. And when M running is false, this no longer runs, the loop exit, and the game closes. Okay, that's how you safely close the game. Next, we're going to have an input system. So the input system here, this is the key pressed. All right. So we have two types of events for keys. One is when the key is pressed down, and one is when the key is released and goes back up. So for key pressed events, we're going to look at the key code, and I have a simple switch here that says this is an example where the W key is pressed. So if the W key is pressed, what you're going to do is set the player's input component's up variable to true, because W moves up. If it's A, you set left to true. If it's if it's right, D, it's right. If it's S, it's down. In a similar way, for the key released, if the key has been released, then you're going to set those input components equal to false. All right? And then in the movement system, you're reading those and making changes to the actual position. It's very tempting. And in fact, most people, when they're programming games, inside the event handling code, they would do something like, say, set the player's position to go up inside the event handling code, like right here. That is very bad practice. You do not want to be setting variables like changing the player's position inside the input code. You just want to set the component variable and let the movement system take care of the input. Alrighty. Then we have the mouse button pressed. So if the event is a mouse button press, we have two cases. One is where we have the left mouse button pressed, and the left mouse button pressed is going to be called spawn bullet here. So inside here is where you would call spawn bullet, and you would pass in the player as the parameter, as well as the XY location of the button press where you actually want that bullet to be fired at. So the XY location of the mouse click can be found by event.mousebutton.x and event.mousebutton.y. And similarly, when the right mouse button is clicked, that's where you're going to call spawn special weapon. Okay, that's it. That was a bit long, but you got the free tutorial, and that will save a lot of time for you, and it will save a lot of time for me. And if we go back here to the website, you have 19 days to do that assignment. So it's a long time. Okay, it goes over midterm break. But just keep in mind that, you want to start that sooner rather than later, because it is not a conceptually complex assignment, but there is a lot of implementation. So you're going to have to do lots of dumb stuff and a little bit of smart stuff. But we're writing a game engine, so that's expected, right? Okay, and my last tip to you is that, here is the actual tip that I wanted to go over, which is the hint for the assignment. So I recommend approaching the assignment in the following order. So at the bottom of the README, here is, please follow this step by step, because it's going to make your life a lot easier. First, don't worry about the configuration file reading until later, okay? Leave that out for a bit. Implement the vec2 class, because the vec2 class is used for everything else. So first, go to vec2, all right? Look at all the functions that you have to do, and once you've implemented them, write some sample code like I did in the slides, like I did in the lectures where I did the live coding, to make sure and test all of your operators. So test the distance function, test the plus equals, test the minus, test all of that stuff before you go on to the next function, or to the next thing. Then you're going to implement the basic functionality of the Entity Manager class. So implement the Entity Manager's add entity and update functions so you can start testing the game class quickly. Do not worry about the update function, which deletes dead entities until later when you get more mechanics working. So just work on add entity and update first, so that you can spawn enemies and spawn players and spawn bullets and start testing. And then later, after you've done the collision stuff, then come back and work on the removal of dead entities. Then you're going to implement the basics of the game class. So once you can implement, once you've implemented the entity manager, then you have somewhere to store everything, okay? So construct a player entity using spawn player. Implement the basic drawing of entities using the render function. So go back into the render function and change it from just the player being drawn to all the enemies being drawn, all the entities being drawn. Then construct some enemies, give them dummy positions like 100, 100, 300, 300, give them some velocities, etc. And then construct a bullet using the spawn bullet function. So you've got that all down, you know it's working, you can test that. Then implement player movement in the user input and movement functions. That'll allow you to move the player around once you've got entities working. Then go back and update, implement the entity manager's update function so it deletes dead entities. Then implement the entity manager get entities by tag functionality. Then implement collisions in the collision detection system and Entity.destroy. So you destroy things if they're dead, and now that you've properly done the deletion of things in the entity manager, it will work. And then you implement the rest of the game's functionality, including the config file reading. So once you know that your enemy spawner works, your bullet spawner works, then you go back and you write the file reading so that you can actually implement it the way that we wanted to in class. Now you can do it out of order if you're very experienced with game programming already, but please, I highly recommend this because we are building things like here's the foundation, here's the walls, here's the doors, and here's the roof, right? You can't put the roof on without the walls, you can't put the walls on without the foundation. So that's that. Okay, so just keep in mind that the live recording of this lecture was done on a Wednesday night. You're probably watching it sometime like on September 30th or after that. So assignment 2 is due just before midnight, so 11:59 p.m. on September 30th. I realized that the university has a new holiday on September 30th. The assignment is still due. Okay, so there's no classes or anything, but it doesn't mean that all work stops. So please take time to respect that holiday, but the assignment is still due because the schedule was made before the university came up with that date for the holiday. So that's just unfortunate. And officially, this class is being held on Thursday, right? The 30th. But officially, Thursday is a holiday at the university. So, if you choose to, that official class has been moved to Saturday. So, you don't have to start the assignment until at least Saturday, but it's there for you, right? So, that's the compromise for me with this holiday, is that please, by all means, observe the holiday, but I'm just making the lectures available to you so you can watch it early if you want to. All right, so that is it for this class. I will see you in the next one when we talk about collision detection and collision resolution for more complex shapes. And that will launch us on our journey towards assignment 3 and writing a 2D platforming game. Thanks.